Okay, so the last lecture we introduced the concept of the hydrograph. We wanted to take some storm event and turn it into a plot of the flow rate versus time from that storm event. We talked about the concept of the unit hydrograph. We looked at actual unit hydrographs and synthetic unit hydrographs. And we want to dig in now to the what we call the NRCS. It used to be called SCS, which was the Soil Conservation Service. It was renamed later to the National Resource Conservation Service. It has a whole set of equations and relationships to get from rainfall to runoff, and it has its own unit hydrograph procedure as well. So let's just start off by going through it. Before we do, though, I guess I want you to keep in mind the biggest of pictures of what we're trying to do with hydrographs. We're civil engineers. We want to design something to deal with the runoff from a storm. We want to drain an area, safely convey the water away from structures or other important infrastructure. In order to do that, we need a flow rate. Whether we're using Manning's equation for an open channel, whether we're sizing a pipe to convey that runoff, or a culvert, we need to know the flow rate. And so one of the things we want to do is calculate the peak runoff from the storm. If our pipe or our channel can handle the peak runoff, it can handle all the other runoffs. We also might want to size a detention pond. A detention pond is going to fill up and take up a lot of volume before it lets some of that out. So we need to know the total volume as well. So if we think about the hydrograph, we're concerned with the peak, how high is it? We're also concerned with how much water is under that curve. It depends on what we want to design. So this is one method. It's a pretty robust method. We'll talk later on in a few lectures. We'll look at like City of Newburgh's regulations and requirements for design, and we'll see how it references this method as well as some other methods we'll learn. And this is one of the more robust methods. We can apply it to larger areas than, say, the rational method. The rational method we'll learn about next time. That's a much more simple method for small acreages. But here we can look at larger watersheds, about 2,000 acres or even more. Once you get beyond that, we typically break things into subbasins where we can apply this method to each one of those different subbasins of area. And so today I'm gonna try a different form of lecture. I'm gonna be copying in the stuff I would normally write down on here. So see how you like it. You might have to pause the video when I copy something in to be able to write it down on your sheet. But so the first part is this calculation of net rain, or precipitation resulting in runoff. So there's an equation here, and the equation looks like this. It says P sub E, which is the net rain, or the precipitation resulting in runoff, is equal to P minus 0.2 S squared divided by P plus 0.8 S. So P is the precipitation from the rain event, how much rain fell. We're saying how much of that actually results in runoff. Remember from the last lecture we looked at a hydrograph and we said we've got our rainfall hyetograph. We could apply a phi index or Horton's infiltration and look at how much is above that infiltration capacity. That's going to be how much of the rainfall results in runoff. This is the same idea. It's not using Horton's or phi, it's using something else. It's got its own relationship. And this is just giving us a total amount of the rainfall that results in runoff. Okay? So that's P and P sub E. What is S? S is the storage capacity of the soil. It has its own equation that looks like this. It says S is equal to 1,000 divided by Cn, which is the curve number, minus 10. So this has to do with how much water the soil can absorb, how well it can infiltrate it before you start getting runoff. And it introduces this new concept of the curve number. The curve number reflects the condition of the watershed or landscape and how susceptible it is to runoff. The higher the curve number, the higher the runoff. And there's lots of resources available to look up curve numbers. In your book, table 8.7.3, I'll show it here in a second. Okay, let's see if we can switch to webcam only. Nope. There we go. All right, so here we go. Let's look at the table in your book. This is table 8.7.3, and you can see if this thing would focus. Well, you can look at it in your own book. We've got the curve numbers over there on the right. They're from 0 to 100, and you can see that for different types of areas. Let's see if I zoom in here. If it'll refocus. Not wanting to focus. Sorry. You'll have to look at the table yourself in the text. But different kinds of areas, you'll see different curve numbers, and they're dependent on something that they call the hydrologic soil group, which are A, B, C, and D. You see in the upper right there, which we'll talk about in a second. All right. Back to that. Let's see if we can get back to this view. All right. So curve number, there's a table. That table and any others are for antecedent moisture condition 2, which we'll talk about in a second. But here's the hydrologic soil group stuff. So this is a very common designation in civil engineering. You'll probably see it quite a bit throughout your career. That these soils in the U.S. are divided between these 4 groups, A through D. So group A is high infiltration, sand, and silts, low runoff potential, high infiltration potential. B is a little bit less sandy, a little more clayey. Group C starts seeing more clays, less infiltration, more runoff, and then Group D are basically clays that don't have very high infiltration potential, and so you'll see a lot of runoff from those. So at least around this area, a lot of our soils are in Group D. I'll show you the NRCS Web Soil Survey, which is a useful tool in a separate video, where you can look at anywhere in the United States, all of the soils have been mapped. And so when you're working on a project and you want to know what the hydrologic soil group you've got is, you can just look it up on the soil survey and see where you're at. So based on the type of landscape you have, like in that table, there's things like quarter-acre residential lots, gravel, lawns in good condition. There's a whole agricultural section for row crops, for small grains, meadow, woods, farmsteads, all sorts of different things. And then based on the kind of landscape it is and then the soil group, you can look up the curve number. The closer that curve number is to 100, the more runoff you're going to see. Okay, so again, like S is 1,000 divided by the curve number. If the curve number was 100, it'd be 1,000 divided by 100, which is 10 minus 10. S would be 0, and so you'd see up here in this equation, P minus 0 over P plus 0 is just going to be P squared over P, which is just P. And so, in other words, all of the rainfall is going to result in runoff when curve number is 100. Versus 0, where none of the rainfall is going to result in runoff. It's all going to infiltrate. Okay? So, then next we have the antecedent moisture condition. So the other thing that's going to matter is if the soil is already saturated, it can't take on a lot more water before you're going to start seeing runoff. And so you've got these different antecedent moisture conditions where if the soil is super dry, it can absorb more. If it's super wet, it can absorb less. So AMC1 is a low moisture. Oops. try that again. Low moisture, moisture condition, where say it's the end of the summer, hasn't rained yet, and so soil's really dry, it can take on a lot. AMC2 is average moisture, and the tables tend to list the curve numbers for AMC2. And then finally is AMC3, which is high moisture, heavy rainfall over the preceding few days. So this is where in the winter we're mostly in AMC3 here in Oregon. And if you need to calculate the curve number for either AMC1 or AMC3, you can take the curve numbers from a table, which is CN2, and convert it to CN1 or CN3 using equations. I'm not going to put them in here, but they're in your text. Equation 8.7.1 and 8.7.2 right there. Page 303 in my book. And then if you have a watershed that has different soil types or land covers, you can calculate a weighted average curve number. So that procedure looks like this, where the average curve number is going to be equal to, say, whatever area A1 applies to curve number 1, plus whatever area applies to curve number 2, plus whatever area applies to curve number 3. Divide that whole thing by the sum of all the areas, and that way you're getting this weighted average curve number that you can apply for the entire watershed. So these are the most basic rainfall relations, where all we're trying to say is how much runoff, or how much of the rainfall is going to result in runoff based on the context, the soil condition, so forth. In the next video, I'll go through a short example problem, and then we'll get into the unit hydrograph procedure.